said, give me a quick check. This is Andy at Chapel Hill.
Hi, Andy.
Okay, we had a battery go bad.
Oh, okay.
Can't really see.
Real facial expressions.
It's this is a forward. Shortened version.
So it's the code for the weather.
Yeah, or any code.
Right here, kind of.
It's just how about the wind?
So I don't know if you want to see
Women couldn't
copy the problem. I don't know if there's anyone you can.
So it's just like
We can see them, can they see us?
Yeah. Okay, thank you. We continue our study of homo-correlation to the NMR spectroscopy. And before I go on, I would like to repeat 2 points of yesterday's lecture, in particular about, first of all, about this picture. I can't zoom in and out. Hello? Hello? Okay. The picture that's given in the notes has a mistake, and what I started doing yesterday, I should correct myself. The Z1212 is the intensity of the peak, which has a frequency omega 12 in F2. Oh yeah. Is that 4.5? Okay. The Z1212 is the intensity of a peak which has a omega 2 frequency coordinate 1, 2 and omega 1 frequency coordinate 2, 1. Do you remember that? In page number 3 you can see that. On previous page it's written down that omega KL and minus times omega Mn or plus times omega Nm. And so we should look for, this is the intensity of that peak. And that means I should really look at the vertical direction from here. All these I have calculated are the intensities of the peak which have frequency coordinate omega 1, 2 in the F2 dimension or omega 2 dimension. Okay, so they refer to the peaks in this line, along this line. And the intensity omega 1, 2, 1, 2 is for 1, 2, 2, 1 transition, which is right here. Okay, 1, 2, 2, 1, which is right here. And that is okay. This is 1, 2, 3, 4. That means 1, 2, 4, 3. And that's this one, also plus 1. And 1, 2, 1, 3 is this transition, which is omega 1, 2, 3, 1. And this is given in notes as minus 1, but that should be plus 1. Okay, oh sorry, it's gone off the column. Maybe I can zoom in now. The zoom doesn't work, please. All right, it works now, thank you. Okay, so this 1213 has a positive intensity, and 1224 has a negative intensity. What we have not calculated, but I have shown it in the diagram here, that the 1224 has a positive intensity, 1213 has a negative intensity, and 1234 and 1212 have again positive intensity. So the correction that I had made in my transparency was correct, and what is given in the notes has to be corrected. And this just says that the zero quantum transition and the double quantum transition will not show up in this case. I would also like to go through this page, which I had not given yesterday, and I have now given as an addendum today. So people here have got this page, but the people sitting at remote at the Duke, have you got a copy of this page today? Have you got a copy of this page?
Only one copy.
One copy. I hope somebody can make a Xerox copy of that and give it to you. And at other centers?
I can bring that in Friday. I can bring this on Friday.
Have you, MCNC, have you got a copy of this?
Hard to keep up with all these things.
There are only 2 people sitting there anyway. Mary, you got a copy on that. Okay. All right. Well, here what I have done is I have not taken away the chemical shift evolution from this analysis. So it's only a J evolution left. And it's then very easy to follow as to what is happening. All right. We have a spin magnetization in the Z direction to begin with. You apply a 90-degree Y pulse, and it is converted into from a Z to a X magnetization when you apply a pulse along the Y axis. At this point, this magnetization starts evolving in the XY plane and rotate with a frequency which is 2 pi j IZB about the Z axis. The operator is IZA, so it's rotating about Z axis with this speed or angle with time t1. This is the angle and this is the time. So what will happen to the X magnetization? It will have an X component with a cosine and a Y component with a sine. And then, as I explained yesterday, that this cosine with an operator IZB, you can expand it and see that it comes out for a spin half as cos pi j_t1. And the sine component comes out as has a 2 IZB outside as a sine pi j_t1. If you substitute that back into this, you have then for the cosine component IXA cos pi j_t1, and for the sine component you get an extra factor 2 IZB. This is the state of the spin before at this point before the second 90-degree pulse. What it says is that we have a magnetization along x-axis, and we have a magnetization along y-axis, but that magnetization has 2 components, one pointing up, one pointing down, because of this factor IZB. And this X component has both of these components pointing in the same direction. And when we apply the 90-degree X pulse on this state of the spin, the X component is not changed because they pulse along the X-axis. This component is changed. The Y component becomes a Z, and the Z component becomes a Y. And this is the point that you notice is a transfer of magnetization from A to a B magnetization. Okay, and this is the interesting step. So what we do need a magnetization which has this feature of +1 and -1. And when we have that, we will be able to do a transfer of magnetization to the other spin by application of a pulse. And this basically is this important step. And this gives us the cross peak, which has a ± in the ω2 direction because of the IZA, and it has a ± in ω1 direction because of the sine component. Okay. On the diagonal, on the other hand, we have a ++ in the ω2 because there is no IZB here, and it has a ++ in ω1 because it's a cosine. And that's the reason for this description of the intensity. And then if we do a sine transform, we will get this in dispersive mode and the cross peak in the absorptive mode. So this is perhaps a more a simpler and better way of understanding the transfer of magnetization from one spin to another. Okay, now we continue our, we come to the 5th lecture, and we continue our study of the homo-correlated two-dimensional NMR spectroscopy. And we will talk about the following experiments in this: spin echo correlated spectroscopy, relay COSY, also double relay COSY, and other experiments, which these experiments extend the spin echo correlated spectroscopy is a replacement for COSY. These extend the utility of COSY. These experiments attempt at increasing the intensity of cross peaks in COSY. Okay, these two. The spin echo correlated spectroscopy, which has basically the same information as COSY, is the following experiment. what is done here is that, you see, we have two 90-degree pulses as before, but our time at which we start collecting the data is shifted by another T1 period, or half of T1. You can say, in other words, what we have done, we have shifted the 90-degree pulse from this point to the middle of T1 period. There are several ways of looking at it. You can say, this is a 2D J-resolved experiment in which I have changed the angle of the 180-degree pulse to a 90-degree pulse. Okay, so basically there are 2 or 3 ways of looking at it. I have written down 2. The result that this experiment gives comes out in this shape, in the sense that the diagonal peaks now come along omega 1 equal to 0 frequency, and the cross peaks lie at an angle of 135 degree from each other. So if this peak and this peak are coupled, we will get a cross peaks which are looking like this, or looking like this. These 2 peaks are coupled. So it has actually, if you look at the information content of a spin-echo correlated spectroscopy experiment, it is identical to a cozy experiment. Therefore, it's more close to a cozy rather than a 2D J-resolved experiment. Okay, how does this happen? Why do we get intensities that look, they are in this kind of diagram? That's very easy to see. Look at the time evolution. We have after the first pulse, the magnetization is the x direction. For half the T1, it will evolve under the Hamiltonian, and we apply a 90-degree pulse. For another half of T1, then it evolves further, and then it evolves for time T2, and then we detect it. This and if we follow exactly the same way as before, we then have the intensity which is given by ZKLMN, a frequency in T2 dimension which is omega KL, and a frequency in omega 1 direction which is difference between the 2 transitions which are coupled to each other. So it gives omega KL minus omega MN by 2. And that means we're taking difference in, and if it is a diagonal peak, then it becomes 0. Okay. There is also, one should think about it here as plus minus, because I can invert the sign of this, and I will still have some value for that amplitude. So I get differences and additions of the 2 frequency coordinates. And the cozy spectrum, which was like this, is transformed to a spectrum like this, where this is the, I have numbered these peaks now for convenience, 1, 2, 3, and 4. These 1, 2, 3, and 4 appear in sexy as 1 prime, 2 prime, 3 prime, and 4 prime. And they're kind of twisted by 45 degrees. Okay, the diagonal peaks which come now on 0 frequency coordinate are all plus, and the cross peak which has this pattern has plus and minus. So if they are not resolved again, they will disappear. The resolution is again a necessity for the cross peak to appear. I hope you can see that. Maybe I should zoom in this thing. Okay, that the cross peak has a plus and a minus here. Okay, that is the quadrant that we call as a negative quadrant, in which the minus sign is used here. Okay, wherever the plus sign is used here, I can write it as a plus here, I don't change that. Then we get another quadrant we call a p quadrant, the plus quadrant. And here the diagonal comes at omega a plus omega x half, average of the 2. Okay, and there seems to be an identical piece of information lying in the other quadrant here. We dispense away with this quadrant by phase cycling. We remove that and don't look at the p part of it. And the advantage is then that, as you notice, that we needed a full, for cozy, we needed a full chemical shift range here in the omega 1 direction. While for sexy, we need only half of that range. And that is the basic advantage of spin-echo correlated spectroscopy. We need only half the range in the omega 1 direction, and we can save some computer space. The phase cycling is, of course, we are going to read about it in greater detail later, but simple things can be seen. For example, we do two experiments with xx plus and xy minus. Then, as I mentioned before, it's like detecting two components of the signal here in the x and y components, and we can decide whether we want to keep the magnetization which is going negative way or which is going in the positive way. And so basically the quadrature detection that we do decides whether we want to keep n part or p part. So it's a sequence like the sum of two experiments for same value of T1, if co-added, will remove the p peaks. The axial magnetization, the magnetization that grows during T1 along the z-axis, also would come in, and that is removed by the following pulse phase cycling. We do experiment x plus, that then after this first x pulse, the magnetization grows along the z direction. And then I apply the second pulse along the x-axis, and I get this component. If I repeat this experiment with a minus x second pulse and add the two, as you see, my information about these components don't change, but of this black part, that is the axial magnetization, is cancelled. And therefore, you see, I was going, by doing the x component, second pulse along the x-axis, I was going to throw away the red part and keep the green. And it doesn't matter whether I do plus x or a minus x for the green. But for the black part, which is along the z-axis, it changes sign. And so simply you can remove the axial peak in such a manner. The advantage of SAXI, as I said before, is that it needs half the data memory in omega 1 direction. This looked to be an advantage in the beginning when we had very little computer memory in the mid-70s, but I don't think this is a big advantage at the moment, except when we start really collecting very huge amount of data even in T1 dimension, but that's difficult because it takes time. Increasing number of data points in T1 dimension is expensive. Okay, but there are several disadvantages of spin-echo-correlated spectroscopy. For example, if there are cross peaks between transitions which are half the spectral width away, then they will fold back into the spectrum. And that is what makes this particular format, if I may say, of taking data unsuitable for nuclear Overhauser effect, because there are certainly NOEs between transitions which are more than half a ppm, 5 ppm away, half the spectral width away. And this 45-degree angle or the 135-degree angle makes it awkward to look at the cross peaks. And that is perhaps one of the main reasons why this experiment is also not so popular. But the real killer is that it gives mixed phases and for all peaks. And people have then devised what is called a filter for that, and I will show you the filter to complete this study of spin-echo-correlated spectroscopy. But one can do these experiments on large molecules, and one gets data which looks as crowded as in COSY, but one can sit down and look at this in a greater detail. This is BPTI inhibitor, 56 amino acid residue peptide that Kurt Wüthrich's group has done a lot of work on. Okay, what is the Z filter? Now, before I can describe to you the Z filter in detail, I will have to actually go through a little bit of the algebra of the spin-echo-correlated experiment itself. But before I go through that algebra, let me just tell you what we are really doing. What we do is we take the magnetization at this point before we start reading it, that is at the end of T1 period, before we start reading the magnetization, we do a trick. We apply a 90-degree pulse along the y-axis. So whatever magnetization was there along x-axis, we will take it in the z direction. And all of the magnetization which will remain in the xy plane will be killed by what we call as phase cycling. Okay? Or there are other ways of doing it. For example, this period, this tau period, is varied between the experiments and experiments co-added. So if there is any transverse magnetization which is processing, it is added at number of places in this procession, and net result is 0. That is called tau jitter. Okay, tau jitter. That is, you co-add several experiments with slightly different values of tau, and the sine and the cosine components which are in the xy plane will sum up and cancel. And then we have only pure Z magnetization left, and we read it by the second 90-degree pulse. And this is called a Z filter. And what the Z filter does, it picks up only IX single operator terms. It picks up only IX single operator terms. If there are terms which are along IY, or if there are terms which are double operator terms, they will be gone out of picture. And this is what is shown here. That is